Hey everyone, and welcome to another seminar of mathematics and high energy physics at Physics Latam. Today we are happy to have Professor Pranav Pandit. He did his PhD at the University of Pennsylvania in 2011 under the supervision of Tony Pantet, and currently he holds a faculty position at the International Center for Theoretical Science of the Data Institute of Fundamental Research in Bangalore, or what is commonly called ICTS. His research involves around mathematics and physics that has arisen from string theory. His work explored aspects of the geometry underlying quantum field theory and string theory using the language of higher category theory and derived geometry. The primary focus of his research has been on categorical structures underpinning the mirror symmetry phenomenon, which is a far-reaching relationship between algebraic geometry and symplectic geometry predicted by string theory. So we are very happy to have him with us today, and thank you for accepting our invitation.
Thanks a lot, Daniel. It's great to be here and great to be connecting with folks in Latin America again. I was there in Colombia earlier this year and I had a great visit. So hi again. I might have met some of you there. Yeah. So the title of the talk was really picked for me by Daniel. He wanted me to talk about modular spaces in quantum field theory and string theory. I don't know how much I'm going to have to say really about the second two parts. I'll try to explain how I think it's connected to quantum field theory and string theory. But I want to start the talk really with the moduli spaces part. So I want to start with saying what moduli problems will mean for me. And then I want to describe a framework to talk about moduli problems. And then we will see some examples of moduli problems. And eventually I'll give you examples that come from topological string theory and some questions in quantum field theory. And I'll end with some questions about how this generalizes to more general quantum field theories. So what are moduli problems? So in the framework I want to talk about them, there will be certain functors. So what are these? So there will be functors from commutative algebras. Over some k. So what is k? I'm going to fix once and for all some ring k. And for simplicity, let's just take k equal to c. So I could have just said over c, but the point is that a lot of what I'm going to say just works over any ring. Some of it will work over fields, some of it will work over algebraically closed fields, but let's just say k is c. So we know what commutative k algebras are. They're just vector spaces with a multiplication that is commutative. And we want to look at constructions which associate to commutative k algebras a set. Right? So what does the word functor mean? That really means that for every, well, first of all, for every commutative k algebra A, I get, so I get some set x of A, which is called the A point. I'm sorry, what do I erase? Let's try this. I get a set which I call the A points of x. And the key point is that saying that it's a functor means that also for every homomorphism, of commutative k algebras, I should get a map x of A, x of A, which we might call x. Okay, so that's what a functor is. I should have thought of how to use my space a little better. Let's see. Let me try to fit it into this screen. So, so why are we interested in these objects? Because let's consider this example. What just happened? It turned blue. Okay. So suppose I have, let's say F underline, which is F1 through FR, collection of polynomials in some polynomial ring. So that's something very explicit. I have some polynomials and n variables. Then I can associate to it this functor. Which is just xf of some commutative algebra A. Well, what is a commutative algebra? It's just something where I can add and I can multiply. So in particular, I can take any polynomial and I can substitute for the variables in the polynomial elements of this ring and ask if I get 0. So this is the set of A1 to AN in A to the N such that Fi of A1 to AN 0 for all I. So that's what you might call the solution set of this collection of polynomials. So you want to study zeros of sets of polynomials, and that's what we're doing. So in particular, you can look at x of k. So these are just the usual k points, right? The C points. So these are the C points. The algebraic variety defined by these polynomials. Zeros of. Okay. So any questions at this point? About the example, about the definition? So all I'm saying is if I have a bunch of polynomials, I can look at their zeros. But I'm not looking at the zeros only over complex numbers. In other words, I could take my polynomials and substitute complex numbers into the variables and see whether they're 0. That would give me a subset of complex n space, C to the n. But instead of just looking at complex n space, I want to look at, I could take other rings, not just the complex numbers, and look at solutions over those rings. And I want to simultaneously do that for all rings. And also remember how if I take the elements of one ring and substitute for them elements of another ring, B, that's a homomorphism from A to B, then how do the solutions of A over A get mapped to the solutions over B? That's what this functor X remembers. Any questions? So I claim that this way of looking at things, this picture is really a Grothendieck's approach to geometry. And the idea is that if I just look at the C points of my X, well, it's just a set. It has no additional structure. It doesn't know how the points in this X of C are glued together. But if I remember this functor, then I can actually recover the way the points in my space are glued together, how they sit with respect to each other in a geometric sense. What do I mean by that? Here's an example. Suppose I want to know what the tangent space to my X is, the set of solutions to these equations, and I want to know what the tangent space is. I claim you can recover it by just looking at this functor. So let's do that. So if you think about what is xf of this ring, Let's consider the ring K epsilon. Let's give this a name once and for all. This is ring KT mod T squared. Right? So it's basically a ring in which there's an element epsilon, which you can neglect. It's like saying that I think of polynomials, but I neglect terms of T squared and larger. So then I can ask, what are the points xf of K epsilon? Well, if you think about this for a second, these are going to be tuples, Z1 plus epsilon W1, Zn plus epsilon Wn. This is an element in K epsilon to the n. Right? Every element in K epsilon is like, this is the set of A plus epsilon B, where A, B are complex numbers, or elements of this ground ring K. So I'm sorry about the sloppy notation, but I'm going to start writing K for K. Okay, so I can ask what this is. I'm looking at elements here which satisfy the equations Fi of Z1 through Zn is 0, which just says that Z1 through Zn is a point, is an ordinary point of this space, is a K point of the space. And 2, Tf, which is the matrix you can build out of the derivatives of f, acting on the vector W, is 0, where W is this W1 through W. So in other words, this is just the data of pairs Z, W, Z in Cn, sorry, in Kn, is a K point, is a point of and W is a tangent vector. Well, I haven't defined what tangent vectors are. I'm appealing to your intuition. You could take this as a definition of tangent vectors to X. Tangent vector to X is an element of, is a K epsilon point of X. So it's a very kind of, you just ask yourself what it means to do algebraic geometry, to study solutions to polynomial equations. You take that statement in the most literal sense and just ask what data you get. Well, what you get from a bunch of polynomials, you get solutions of those polynomials in any ring A as A varies. And that encodes, for example, things like the tangent space of the space you want to study. So let me just remark that you can observe, that you can think of this in a slightly different way. Namely, if you set B to be K x1 xn modulo f1 through f, did I say f1 through fn? It should be fr. I don't want the same number. X1 through xr. And so then this xf of A is just homomorphisms of algebras, K algebras, from B to A. Because what is the information I need to give a homomorphism of algebras? I have to tell you where each point xi goes under the homomorphism. So that would go to a point ai. But then it has to factor over the ideal f1 through fr. Each fi has to get mapped to 0, which is just saying that if I evaluate fi at the point a1 through ar, I get 0. So this is a sort of more abstract way to just say what I said. But this version works for any algebra B. This makes sense. For any B commutative algebra. So you get a functor spec B by definition is the functor Hom commutative algebras over K from B to blank is a functor in commutative algebras over K to sets. Right? I can just look at homomorphisms out of B into any A, and that gives me a functor. I call that functor spec B, spectrum of. So these are called affine schemes. So are there any questions so far? So we started with a very simple motivation. We just want to study zeros of polynomials. And we saw that we can reformulate it as studying a rule that assigns to every ring the solutions of those polynomials in that ring. And we re-express that by saying that to every ring A, I'm looking at homomorphisms from some fixed ring into that ring. A functor of that form we call spec P. And these are called affine schemes. Any questions? This is really the starting point for what we're going to do. So, okay, so if there are no questions, so what is the idea? So I'm going to talk about moduli spaces, but I want to provide a setting where we can formalize what it means to have a moduli problem and what it means to solve it or to find a solution to it. So a moduli problem will typically be just given by a functor. But just having some random functor I mean, that functor is not necessarily a very geometric object. We just saw that if I have a functor of a special form, like for example, of the form spec P, then it has some geometric content. For example, I can extract from it things like a tangent space. So inside the collection of all functors, there are nicer functors, which you might call, for example, the nicest ones you might call affine schemes, the ones I just defined. But you would like to build more general functors out of affine schemes by gluing. Those would be called schemes, and then from schemes you can build still more general things, on which you can still do geometry. For example, you would like to talk about tangent spaces, you would like to talk about sheaves on them. Well, you can talk about sheaves on any functor, but you'd like to talk about geometric constructions which behave well. So you identify this nice subcategory of geometric things inside the category of all functors. And given a moduli problem, the basic question is this moduli problem represented by a functor in this nice geometric class? That's the basic structure of the study of moduli spaces in algebraic geometry. So you have a good solution to your moduli problem when you have found a nice geometric functor which is equivalent, which is isomorphic to the moduli problem that you saw. Okay. So, well, I've talked about, so far I've just talked about the objects, which are these spaces, these functors. Now I want to talk about, well, to study any kind of mathematical object, you need to understand the maps between them, right? So I want to talk about maps between these functors. So functor is just a fancy word for what I just described, that for every commutative algebra, I'm assigning a set. And for every map of commutative algebras, I have a map of sets. Now, suppose I have two such guys. Then I can ask the following question. I can consider maps between them. A map f from x to y is the following data. The collection of maps of sets from the a points of x to the a points of y, such that what you'd expect for any . If you change the ring, which is you substitute elements of one ring to another, then you get a commutative diagram. Okay, so these are what the maps between things are. So we'd like to know what maps between affine schemes are, for example. That's the first question that comes to mind. So let's try to answer that question. So the context, we can put ourselves in a much more general context by replacing commutative. What I'm about to say is nothing special about commutative algebras. I can replace commutative algebras over K by any category. And then you have the, so if C is any category, so category is something that has some objects and morphisms between them, and you can compose morphisms. Then you can form the opposite category. C op by reversing arrows. So it's going to be more convenient for me to write things in terms of the opposite categories, just for psychological reasons. So we have you have a functor which goes from C to functors from C op to sets. Right? Functors from C op to sets. This has a name. It's called pre-sheaves on C, which sends x to the functor hx, which is by definition just forms from any object into x, maps from any object into x. Right? So for every object, I have this functor, and the Yoneda lemma says the following. It says that Holmes between two functors. So I just defined what map between functors is on the left side. So maps between functors from hx to any f is isomorphic, is in bijection with just the x points of it. And what is the map? The map just sends, it takes, what did I call them? I call them capital F. Will we stick to that? It takes capital F, goes to f sub x of identity of x. Oops, sorry, but I used f for something else as well. I'm sorry, I made a big mess with the notation here. Let's just stick to phi. So phi from hx to f gets mapped to phi of identity of x, phi x identity. So Yoneda lemma says that this map is a bijection. So if you're bored for the rest of this talk, I recommend trying to prove this. It's very elementary. Once you know what the map is, which I've given you, it's extremely elementary to prove this just by using the definition on the left. So what does this buy us? So let us take, in our example, we want to take, let's see if I can put this here. We want to take C equal to commutative algebras or opposite. So what does this tell us then? It tells us that Hom from spec A into any x is isomorphic to just x of Z. I'm just applying this with C equal to commutative algebras or. In particular, Hom from spec A to spec B is just isomorphic to form of algebras from B to A. In other words, I defined spec A as some functor, as some rule that assigns to every algebra B some set and so on. But just by this general nonsense from category theory, you know that the maps between these two guys, spec A and spec B, are just homomorphisms of algebras. So among all these crazy functors, these functors are particularly nice. You can understand what they are and what maps between them are very concretely, which is maps of algebras. Any questions? Okay. So I wish I had a little more room here, but I don't, so I'm going to go to the next slide. So sort of conclusion, what's our conclusion? We can define, the conclusion was, so let me just remind you that Hom in functors from spec A to spec B is just Hom in algebras, commutative algebras from B to A. And so if I define affine schemes to be the full subcategory of functors consisting of functors of the form spec A and spec B, then what we've just concluded is that affine schemes over K of is just commutative algebras over K. Okay, so the idea is to, as I said earlier, the idea is build a class, a nice class of geometric functors by gluing affines and given a moduli problem, which is just a general functor, in other words, a moduli problem, we can ask if it lies in this geometric class. So that's the general scheme of moduli problems. So I'll give you some examples soon enough. So I don't know, one thing I could do is to explain how this gluing looks in some, I could just say gluing and stop, or I could give you an idea of what gluing means, at least for schemes. So maybe I can ask the audience, or Daniel, what do you think? I mean, if people want to hear, would people like to hear about how the gluing works? Anyone in the audience, you can unmute yourself and ask.
Well, I think it's it was already covered in the algebraic geometry course, but I don't know if people want to see it. Maybe if somebody wants to see it, just raise the hand quickly. The gluing of schemes. Okay, nobody raised the hand.
So if no one wants to, I'll just say very briefly what I mean by geometric functors in this special case, and then we go to the examples and so on. So I won't go into detail. I'll just say very quickly what I'll remind you, since you've already seen it, what schemes are. So example of a geometric class with functors might be schemes. So what are schemes? So schemes are functors that have so X from commutative algebras over K to sets is a scheme, not an affine scheme, but a scheme if it is glued from affine schemes in a very specific sense. If X is local, which means it's a sheaf for the Zariski topology, and it admits an atlas, which is a so when you study, for example, manifolds, you can try to cover a manifold by its open sets. Sorry, by open sets which are locally like balls in Rn, and so that jointly the map from those collection of open sets of Rn is surjective onto this thing. So here it's an atlas is a map from a disjoint union spec AI to X, where each spec AI sitting inside X is which is a epimorphism with each spec AI contained in X. The risky open subform. So I didn't tell you what a sheaf on this, what it means for X to be a sheaf, and I didn't tell you what it means for a subfunctor to be an open subfunctor. But that's the spirit of the definition, at least. I hope it conveys how one goes about this. You can look at, you can define a notion of an open subfunctor. In other words, collections of, for every A, you can look at collections of points of X of A that form a subfunctor. And then you can say what it means for that to be open. It's obvious how to do it for things of the form spec A, and then one uses that to globalize it. So that's the idea. And from that, you can define what schemes are. They're things that have an atlas, a Zariski atlas. Okay, so let me give you some examples of moduli functors. I don't know which example. This is, I think, example 2, because the first one was like spec A. So here's a functor. You can take, so maybe this is the functor Pn from commutative algebras sets, where Pn of A is the set of maps from A direct sum n plus 1 times mapping epimorphically onto some L, where L is a projective module, A module over A of rank 1. This is trying to capture the idea of realizing projective space as a Grassmannian of lines inside a fixed vector space, but you want to globalize it for different rings A, and this is the functor. And you can ask, is this an affine scheme? It's not, but it is covered by affine schemes. It's covered by, in fact, maybe before this I should have said what AN is. An is spec of the polynomial. So it's covered by a bunch of copies of An. And so this is an example of a moduli functor. I can define the moduli of such quotients. And this moduli functor has a nice solution, which is represented by a scheme. Namely, it has an atlas covering it by ANs, which I'm sure you're all familiar with. Let's do a more fun example, more interesting example. So I could consider, so fix a vector space V, fix a finite dimensional say k equal to C. Okay. And let's call the vector space V. And I want to consider the moduli space of associative algebra structures on V. So this would be M alg M alg V in commutative apologies. From commutative algebras for K to sets. So what is this functor going to be? It's going to be defined as follows: M alg V of some A is isomorphism classes of associative algebra structures on V tensor A. Sorry, I apologize. Isomorphism classes of associative A algebra structures on V tensor A. Is it clear what that means? I take V tensor to the A. I want to define a binary multiplication on V tensor A, which is a map of A modules from V tensor A, tensor V tensor A to V tensor A. That's what an associative algebra, A algebra structure on V tensor A means. You should think of this as a family. You should think of this as isomorphism classes of families of A algebra structures on V, sorry, of algebra, associative algebra structures on V, parameterized by spec A. Right? So this is what it would mean to formulate the question: what is the moduli space of associative algebra structures on a given vector space? I can ask, can I describe all associative algebra structures, and can I describe them as a space, as a set of solutions to some polynomial equations somewhere? So the best possible thing you might hope for is you might say, oh, is this an affine scheme? Is this representable? Is this of the form spec A? And you quickly find that it's not in general, but that would be a reasonable question to ask. Is it given by some solutions to polynomial equations in some affine space? Next better thing to do would be to ask, is it a projective variety somewhere? Or is it a quasi-projective variety? Is it some open subset of a projective variety? And so on. So projective varieties, of course, would be subsets of Pn, which I've just defined here. So this is the kind of question you can ask. And this is a prototype for those in physics. I'm going to describe a kind of variant of this later, which will amount to asking for deformations of the category of branes in some string theory, in some topological string theory context. Okay, are there any questions? Yeah, I don't have a good sense for what people's background is and so on and what people are interested in. So feel free to interrupt and ask questions or say it's super boring and you would like to hear something different. I'm flexible. Okay. So there are two kinds of questions you can ask. You can ask a global moduli question. What's the moduli space for all structures of a given type? And then you're asking if that's representable, if that's just can be described as some scheme or some affine scheme or something more fancy. But I can ask a simpler question. I can fix a point in this would-be moduli space. For example, I could fix an associative algebra structure and ask what are all the nearby associative algebra structures. In other words, I'm trying to describe just a neighborhood of a given point inside some would-be moduli space. That should potentially be an easier question. And you can formulate that as follows. So given, so let me talk about a little bit about formal moduli problems. Actually, before that, I had a remark that I wanted to make. I don't know if I can go back to the previous screen. I think there's room in this slide. Maybe I can make the remark here. So let me just remark. We actually have a functor. Here we have a functor M alg V tilde, which actually goes from algebras to categories. And I obtained my functor M from M tilde by taking the isomorphism classes of objects in this category. By passing to iso classes, you get two sets. So this will be important later because we'll see that actually forgetting this information that you had a functor to categories and not just to sets causes a lot of problems. And there's a much more beautiful theory when you don't forget that information. Okay. So yeah, let me just say a word about formal moduli problems. So these will be functors. So given x as before, and suppose I'm given some point x inside x of k, a k point of x. Okay. So if k equals to c, I have some algebraic variety given by some solutions to polynomial equations, and I fix a point in that space. Then I can define a new functor x hat at x from augmented commutative algebras over k to sets where x hat of x on some a mapping to k, some augmented algebra, is just defined to be the fiber over x of x of a mapping to x. I can look at all elements, all A points of X that map to the given K point of X. So we already encountered this once. We saw that if I look, so for example, K epsilon is augmented. And we saw that, so this fiber X hat X of K epsilon, well, I fixed a point X and X of K that was fixing the point right at the beginning. And now I'm looking at all K epsilon points, in other words, tangent vectors, whose base point is the given point X. So in other words, I'm just looking at the tangent space at X of X. Right? So I can define this new gadget that sees things around the fixed point X. And I can restrict to a sufficiently small neighborhood of the point by asking that I only allow augmented commutative algebras that are sufficiently small. So this is the Grothendieck-Schlesinger approach. To deformation theory. In this case, what am I deforming? I'm deforming X. Is that you define, you restrict to Artinian, so small algebras, where by small I mean the following: finite dimensional over K with unique maximal ideals. Which is the kernel of A mapping to K. Okay? So I get a functor X hat X going from small algebras okay, also known as Artinian commutative algebras to sets. And you can characterize, you can ask if my X was nice and geometric, if it was a scheme, for example, what properties would this X hat X have? And you could list some axioms, and they're called Schlesinger's axioms, which describe functors that arise in this way. So Schlesinger, here's some axioms on functors y from small commutative rings sets, which should be satisfied for y of the form X hat X with X geometric. For example, X is scheme. Right? So we can use these axioms. We can start with any functor that satisfies these axioms and try to ask if it is represented by some geometry. So before we go to a break, let me just give you an example of such a functor from Artinian rings to sets, which is in some sense universal. So for this, I need to make a definition. Actually, maybe I should make the definition first. Definition. So we have this notion of a differential graded Lie algebra. This is some G, which is a direct sum. Let's say K vector spaces, graded K module. differential D mapping gk to gk plus 1, d squared equal to 0, a bracket going from gk tensor gl, gk plus l, satisfying some axioms. Always get these signs wrong, so I wrote it down somewhere. Mm-hmm. Let me just, I just said plus cyclic permutations. And D of x bracket y satisfies the Leibniz rule. So what a differential graded Lie algebra is. It's a vector space with a Lie bracket which is graded and is compatible with the differential. So if you have a differential graded Lie algebra, you can define you get a functor or the Monod-Cartan functor from small commutative algebras over K to sets, which is defined as follows. So MCG of A, but remember A is it's an augmented ring, so it has a unique maximal ideal, and so this is just going to be solutions. So X in G1 tensor MA, the maximal ideal, such that dx plus half xx equal to 0. This is the Monod-Cartan equation. Modulo some group. So what is this group? Well, note that G0 acts as a Lie algebra on G1 by x goes to bracket x from G1 to G1. So I can exponentiate this infinitesimal action. So I have an infinitesimal action of the Lie algebra G0 on the vector space G1, and I can exponentiate it and look at x of G0 tensor ME. So this is something that physicists do all the time. Most of the time in physics, you present symmetries by their infinitesimal generators. So the infinitesimal generators are just bracketing with x. So I have this functor I can define for any differential graded Lie algebra. And in some sense, the claim is that this is the universal example of such functors, because the formal neighborhood of any moduli problem can be described by some variant of this functor. Okay, so let's see this in action. So are there any questions first? We can go into a break soon, but I'll just give one or two examples and go into. Any questions about the definition of the Monod-Cartan? So if not, let me continue. So we can go, maybe I should just say one more thing here. that so you should keep in mind, really concrete examples of these small commutative algebras. So you might want to think of A equal to main examples, if you like, in some sense, is A, the augmented algebra. Well, what is it? Is equal to just K T mod T to the N, mapping to K. Okay. So you're looking at deformations parameterized by spec of K T mod T to the N, which concretely means that you're trying to look for a point equipped with a tangent vector and a 2-jet, an infinitesimal curve passing through the point, which remembers the Taylor series up to order n-1. That's what the data of a kt mod T to the N point of my space is. And so again, here you can sort of explicitly substitute the maximal ideal here is just T to the N. So it's something very concrete. So for example, you could take the example M-alg and compute it at a point, right? So you could look at def-alg, right? A, which is the completion of M-alg B at some point A, where A is some associative algebra structure. With underlying vector space V. So instead of the more ambitious problem of constructing the entire moduli space, I can ask, what are the deformations of one particular algebra? What are the points that are near one particular algebra? And in particular, I can ask, what is the tangent space at, so this def-alg A at K epsilon, well, we know this is the tangent space of this moduli space of algebra structures on V at the point A. And what is this equal to? Right? So this is an exercise you can actually do very explicitly, because what is an algebra structure? An algebra structure is just a map. It's just a map mu A from V tensor V to V, and an identity map from K to V, satisfying mu A of mu A tensor 1, sorry, minus mu A 1 tensor mu A, 0, this is associativity. And identity, plus identity axioms. So if you want to study deformation of this over K epsilon, you're just looking for to perturb mu A, or to write mu A deformed is mu A plus epsilon times some theta, where theta is also a map from A tensor A2. So the question is, what conditions on theta? So I have to impose the equations of my moduli problem. The equations are this. This associativity equation is the equation, the polynomial equation that we're looking for. It's a quadratic equation. And we have to impose this quadratic equation to find out what conditions we have on theta. And then we have to identify we have to take isomorphism classes of deformations. So we have to identify two deformations if they're equivalent. So we can do that exercise, and that's an exercise. So I encourage you to try. So you'll find the following. So you should find the following thing, that def-alg A of K epsilon, the tangent space, is given by something called the second Hochschild cohomology of A. So this goes back to Gerson, Haber-Schach from the 60s. This and much more. But in fact, one can do much more. One can describe all deformations, not just deformations over K epsilon, which is this first order deformations. But you can ask, given a first order deformation, can I lift it to second order? You can go order by order in perturbation theory, so to speak, and try to expand in power series. So in the previous slide, I could do, instead of just looking at mu a plus epsilon theta, I could look at mu a plus t times theta plus t squared times theta prime modulo t cubed. So plus O of t cubed, and you ignore quantities of order size t cubed, and try to impose these equations and see what you get. And in this way, you can try to construct this the space as a space of solutions to some equation. But in fact, you can find it kind of in one shot. Namely, you can define this object called C star of A. We call this the power complex. So what is this? This is going to be a chain complex. Sorry. I apologize. Let's check the Okay, so let's try again. So we go from A tensor plus 2, 3, 8, 8, we get a complex like this. So the complex of 3 A tensor A by modules. And from this, you can construct this thing called the cohomological Hochschild complex. Which is basically in A tensor A by modules, A tensor A of A tensor A of modules from this guy A. You can record A as an AA by module, and you can define this Hochschild complex. The cohomology groups of this complex are called the Hochschild cohomology groups. But this guy is a differential graded Lie algebra. If you shift it by 1, is a differential graded Lie algebra. And this def alg A is just isomorphic to, let's call this guy G, is isomorphic to this Morakatan of G. Okay. So the Morakatan of G gives you an explicit way, given some purely algebraic data, a differential graded Lie algebra. It gives you a way to write down some equation called the Morakatan equation. We saw this equation. It's a very simple equation, just a quadratic equation, whose solutions modulo some group action after you quotient by group action give you the certain moduli space, formal moduli space. And what this is saying is that this particular moduli problem of deformation of algebras is of that form. It's Morakatan of some differential graded Lie algebra. Now the amazing thing is, so at some point yeah, maybe I just say one more. So second example. So we take X to be some complex manifold. And E some holomorphic vector bundle. So what is this? This is given by some underlying underlying C infinity bundle plus del bar E operator going from sections of E, sections of E tensor omega 1, and satisfying the Leibniz rule. An integral. Right, so we can describe a holomorphic structure on a vector bundle by giving an underlying C infinity bundle and then giving this del bar operator. And so again, you can ask, you can look at deformations of the holomorphic structure. So this gives rise to a functor def E, again from small algebras. So I'll let you formulate the exact definition. They're just small perturbations of this del bar. And again, there's a differential graded Lie algebra G, which is going to be A01 x of end E, comma del bar, with the commutator bracket. This is smooth 0-1 forms. With values in E. And it turns out that def E is MC of G. So you can say you've solved this formal moduli problem. You've found a way to describe deformations of your vector bundle. So again, this is an exercise to think about this. I think it's, well, doing the entire exercise may not be trivial, but at least computing the tangent space, let's say compute def E of K epsilon and show that this is isomorphic to endomorphisms of. So we see a pattern here. We have a way to describe moduli spaces by writing solutions to Markatan equations, at least locally. And then there's a more global question, how to describe global moduli problems. So these two examples, again, this goes back, the deformation theory, this goes back to Kodaira, Muranishi in the 1950s and 60s. And then people slowly realized that in all these situations, you have some differential graded Lie algebra, which controls the description of the moduli space deformations of the given structure that you're studying. But to make this a theorem requires us to move out of the realm of ordinary algebraic geometry and into derived algebraic geometry. And this will also be necessary when we consider generalizations of these problems, which are relevant to, say, physics. So for example, these vector bundles, holomorphic vector bundles, I can think of them as being examples of B-branes in topological string theory. But more general B-branes are given by complexes of vector bundles. So they're given by objects in what's called the derived category of coherent sheaves. And so you might ask, can I deform objects in the derived category of coherent sheaves? Now, what's a B-brane? A B-brane is, well, it's a boundary condition. So it's really a two-dimensional boundary field theory. So in a certain sense, studying deformations of holomorphic bundles or general or complexes of bundles is an example of studying deformations of boundary field theories. It's the simplest baby example where you can try to study this. And similarly, the previous example I showed you, deforming this algebra, associative algebra, has a generalization where you deform a differential graded algebra or an A infinity algebra. And those algebras control, again, a topological field theory. So it's like deforming the bulk theory in this case. You're studying deformations of some bulk two-dimensional theory. So again, these are toy examples where you can really try to understand deformation theory of kind of baby quantum field theories as a toy model to understand more general moduli spaces of quantum field theories. So I see a question about reference. Maybe I'll ask you what exactly you want the reference for, but maybe we can take a break now and resume in like 5 minutes. Yeah. Okay, so I'm going to now make a kind of a sharp phase transition. So we discussed some motivation, some examples of moduli problems, and now I'm going to discuss analogs of these moduli problems in derived geometry. So I want to just say what I mean by derived geometry. So I'm going to be much more sketchy in this part of the talk. The purpose of describing schemes and so on quite explicitly was to say, this is something you can do. It's motivated by very concrete things. And now I'm going to take a step into kind of a much more abstract world. But let me say a couple of words of motivation for this. So let me put over here homotopical math. So what we saw in all the examples we constructed of these modular functors is we constructed some functor, say from rings to sets, like associative algebras or the Morikawa functor. But in every case, the set that I got was obtained a set of equivalence isomorphism class of objects in some category, right? So in other words, by passing to isomorphism classes, I forgot some data. I forgot the fact that there could be multiple isomorphisms between objects. In particular, if I take one object, it could have a lot of isomorphisms to itself. In other words, a lot of automorphisms. And those automorphisms are called symmetries. And by doing this, I've completely forgotten symmetry. And it turns out that a lot of the questions about modular problems behave much better when you remember this extra symmetry. So how do you do that? You replace every set inside by a space. So we're going to replace sets by spaces. So like you can think of topological spaces. And we're going to replace equality by paths in these spaces. Right? So elements of a set will get replaced by points in some space. Equality of two elements gets replaced by a path between the 2 points. But now there can be many paths, many ways in which 2 points can be equal. We're going to replace vector spaces or modules over some K with chain complexes. Over K. So I'm assuming everybody knows what this is. We already saw a chain complex a while ago. So chain complex, maybe I can quickly say, it's just collection co-chain complexes, let's say. These are just collections of vector spaces, ek minus 1, ek plus 1, and so on. Some maps D with D squared is equal to 0. Okay. And so on. So every classical notion of mathematics has a homotopical notion. You can replace sets by spaces, equality by paths, vector spaces by chain complexes. So commutative algebras, okay, would get replaced by differential graded commutative algebras. So differential graded commutative algebra is basically a chain complex with a multiplication that is compatible with the differential and is commutative in a super sense, in a graded sense. So derived geometry is just geometry in this context, right? So if I want to take the notion of a scheme and upgrade it to this homotopical or derived world, what should I do? I should replace my rings by differential graded rings, and I should replace my sets by spaces. And I should comment that you can get back to the ordinary world by taking connected components. If I have a space, I can take connected components and I get an ordinary set. If I have a cochain complex, I can take its homology groups, and I would get a vector space, ordinary vector space, and so on. So the right-hand side is a much richer world. It has much more information in it. And remembering this information turns out to be the key to having clean solutions to various problems. And you can always get back to something concrete by taking connected components or by taking H0. So a derived p-stack is just a functor, and well, I should strictly speaking say infinity functor, but it's a functor which assigns, which goes from commutative differential graded algebras over K with cohomology of A equal to 0. So hk of A equal to 0 for K bigger than 0, sorry, hn bigger. So these are called connective commutative algebras. And strictly bigger than 0, you shouldn't have cohomology. Although cohomology is in negative degrees, and my differential is increasing the degree. So these are called connective differential graded algebras, two spaces. So this is a pre-stack or a moduli problem, or derived moduli problem. And inside the world of derived pre-stacks, you have classes of objects which you identify like schemes, which are nice objects. And if anyone wants a precise definition, I can discuss it maybe at the end of the talk. But I don't want to get derailed there at the moment because I'd like to give a couple of examples that connect to the physics which I promised. So let me just say the following: that inside pre-stacks, you have for every n, you have the notion of n geometric stacks. So -1 geometric is just affine schemes, which are represented by a single differential graded algebra. And then you can build more and more complicated things by gluing, except gluing in this homotopical world is a much more complicated thing. You can do much more complicated things than you can do in the ordinary world when you talk about gluing. So these objects are much more complicated. I don't want to get into very precise definition just now, but I can give you a definition if anybody wants to know at the end. Right? So the basic question is, given a derived moduli problem, is it representable by an n geometric stack for some n? That's the kind of question you can ask. You can also do the analog of formal moduli problems. So these are functors. So this definition I'm giving is Moduli. So these are functors x from small again, it's some analog of the previous definition. So like with finite dimensional cohomology groups and a unique maximal ideal, commutative differential graded algebras, which are automatically augmented to spaces such that when x of a point, x of k, is contractible, so if I took the formal completion at a point of any modular problem, I would have this property. And for pullback squares like homotopy pullback squares, A, B, B prime, A prime with pi0 mapping surjectively onto pi0 B prime, pi0 A mapping surjectively pi0 prime, X A, X B, X B prime, X A prime is a pullback square. And I'm just writing this definition, even if you don't know what homotopy pullback squares are, to say that the definition is extremely simple and very natural. Okay? So you have this notion of formal moduli problems. Now it turns out that if G is a differential graded Lie algebra, then there is a functor. Let me write this as curly MC of G from small algebras to spaces, such that the old MCG that we wrote, such that MCG is just pi0 connected components of our curly MCG. Okay, in fact, I can tell you what this is. So an n simplex. So for those who know simplicial sets, you can think of spaces as simplicial sets, and an n simplex in MCG of A is a solution of Monopattern in G tensor differential forms in the n simplex tensor maximal. Roughly that's the idea. So you can actually define a simplicial set or a space from a differential graded Lie. Now here's the amazing thing. So there was this philosophy which was motivated by this thing I told you, that when you study definition of associative algebras, so Gersnauber and Schack did that in the 1960s, and they found this differential graded Lie algebra was in the background. And similarly, when you study deformations of complex structures and holomorphic vector bundles, you find this another differential graded Lie algebra. And then also for deformations of complex structures on a manifold, again, you find differential graded Lie algebra. So this led to this philosophy that every differential deformation problem, every formal moduli problem should be controlled by some differential graded Lie algebra. But now in this context of derived formal derived geometry, you can make this into a theorem. So theorem, so before it was only an art or a philosophy which was advocated by many people. Drinfeld, Fagan, Kontsevich, Delin, many people advocated this idea, but then this became a theorem. That formal moduli problems are actually equivalent to differential graded Lie algebras. In other words, for every formal moduli problem, there is a differential graded Lie algebra. And in this direction, the construction takes G to this curly MCG. And in the other direction, given a formal moduli problem, since my functors map to spaces, and these spaces come with a natural base point, I can take the loop space of that space. So I can take the tangent space of the loop space of X. Now the loop space of X is a group. And so you expect the tangent space of a group to have a Lie algebra structure. And so that's morally why you have a Lie algebra whenever you have a formal moduli problem. Because you can take the loop space of the formal moduli problem by taking loops at the fixed base point, and you you can take the tangent space, by which I just mean evaluate on k epsilon, as we did before, and you find this becomes a theorem. This philosophy became a theorem. So we know that differential graded Lie algebras are controlled, control the formal deformation theory near a point. And then the global question is whether, given a modular problem, a global modular problem, can I find an n geometric stack, that is isomorphic to that modular problem? Okay. So that's the sort of background in this derived geometry. So what is the problem that all this helps us solve, especially connected to physics? So to explain this, let me give you two modular problems, and generalized modular problems that we already saw. So if you take X, let's say some compact, some projective variety over C, smooth projective variety. Okay. So that in particular, that's a Kähler manifold. So then I can associate to this. Let me just say this implies that X is scalar. And physically speaking, I can think of the scalar manifold as some target space for a sigma model, and then do some path integral quantization, and I will get some supersymmetric, some superconformal field theory. And that superconformal field theory has two topological twists called the A model and the B model, the A and B twists that Witten described. And now you can ask, can I describe these two topological field theories explicitly, right? So these two topological field theories, a Kähler manifold is given by a triple X with a complex structure and a Kähler form. And this is symplectic structure. Now I can produce from this data two objects, which I'm going to explain to you how it is connected to what I just said about topological field theory. So if I start with X, I can produce from it this category perfects. This is a differential graded category. What that means is that Hom in perfects of E to F, E and F are two objects, is a co-chain complex. And composition is respects multiplication. Respects the differential. So this is a differential graded category, and this is called the category of B branes. Physically, it's the boundary conditions. It's the B branes on X. These are boundary conditions for the B-twisted topological sigma model. With target X. And so what are objects of perfects? I won't really be able to tell you the whole definition of perfects. I mean, it's not very hard to define, but I don't have the time. So objects of perfects are, roughly speaking, bounded complexes of holomorphic vector bundles. On X. Okay. So these are B branes on X, which are from the worldsheet point of view, these are like boundary field theories defined on a two-dimensional worldsheet with boundary. So you can argue, you can make some physical arguments why those correspond exactly to bounded complexes of holomorphic vector bundles on X. So a category. And to the pair X, to X again, which is, remember, it has a complex structure and a scalar form, you can also associate something called the Fukaya category of X. So again, I won't tell you in much detail how to define this category. In fact, it takes thousands of pages to make precise definitions. But let me just tell you roughly what the objects are. The objects of this category are Lagrangian submanifolds, so decorated. I can get away by just saying decorated. It includes all possible things that could go wrong with my definition, are included in this decoration. So decorated Lagrangian submanifolds L inside X, and Hom L1, L2 as a graded vector space is just the direct sum of the intersection points. But there's some, the differential is non-trivial and is defined by counting holomorphic disks. Differential and multiplication, composition, etc. is given by counting holomorphic disks. And in fact, strictly speaking, this thing is not a DG category, not a differential graded category. This is an A infinity category. But every A infinity category is equivalent to a DG category. Differential graded category. Okay. So this holomorphic disk, so you have two Lagrangians, L1, L and L prime, so L1, L2, and the differential, say, involving two intersection points X and Y is given by counting pseudo-homomorphic disks with boundary on L1 and L2. So it's some category, and this category has the interpretation. This is the category of A branes on X, which are the boundary conditions for the A twisted sigma 1. Right? So really the problem of deforming vector bundles that I talked about earlier was a problem of, has a generalization, which is deforming complexes of vector bundles and understanding the moduli space of complexes of vector bundles. And that one, we studied a special case where you have a single vector bundle, but you could ask for complexes of vector bundles. And that becomes much harder and much more complicated because when you talk about equivalences of vector bundles, there are just maps between them, isomorphisms. But when you have complexes of vector bundles, you have maps between complexes, but then you also have homotopies between complexes of homotopies between maps of complexes and homotopies between homotopies and so on. So the point is that the space of complexes is really a space, and it can have higher homotopy groups. And that's what makes it a much more complicated question. So just like we studied moduli of vector bundles, you could try to study moduli of A branes. And all of this has a common generalization, which is the following thing, that if there's another theorem, there's a theorem called the cobordism hypothesis. So what I'm going to describe is a special case of the cobordism hypothesis. This is I'm going to take D equal to 2. And in this case, it's due to several people. with Segelman, Costello, and of course Lurie. So Lurie proved the general case. For all dimensions. And so what does it say? It says the following, that two-dimensional extended topological field theories are equivalent, meaning the data of a two-dimensional extended topological field theory is completely specified by giving a smooth and proper DG category, differential graded category. Right? So the left-hand side, these are basically functors. The definition of the left-hand side, these are functors Z from some category of Bordisms. So this is Bord 2 in this case. Bordisms of manifolds, it's an infinity 2 category, two DG categories. And this this arrow just sends Z to Z of a point with some trivial figure. The Z you should think of as the partition function, and you should think of this arrow as something that assigns to every manifold of dimension less than 2 an invariant. So to manifolds of dimension 2, closed manifolds it assigns numbers. To closed manifolds of dimension 1, it assigns chain complexes. And to points, it assigns DG categories. So the point is that to know this extended topological field theory is the same thing as to know a certain category. And if the category has an object called a compact generator, so definition, C be a DG category with all colimits. Maybe I should be more precise. Say presentable. And so if you have an object E which you should now think of as a brane, as a boundary condition in some theory, E in C is compact if Hom E to blank commutes with direct sums and is E is a compact generator if Hom EF is contractible, implies that F is contractible. F is 0. Okay. So why am I mentioning this? Because if all this stuff about differential graded categories seems sort of very complicated, we can really reduce to something very concrete. So if E is a compact generator, then we get a map from C to modules over A, where A is the endomorphisms of E, by sending an object F to Hom EF, on which you have an action of Hom EE by just precomposition, which is A. So the statement is that this is an equivalence. So this A, what is A? A is a differential graded Lie algebra. Sorry, differential graded associative algebra. And it's a fact. So theorem on the log of any reasonable scheme has a compact fit. So the upshot is that any scheme, nice enough, but nice is a very mild condition, is affine if you allow non-commutative rings. DG rings, differential graded rings. You can write the category of modules, quasi-coherent sheaves on any space as the category of quasi-coherent sheaves on X. And by the way, quasi-coherent sheaves is just completion of perf X under coordinates. So there are two questions here. You can fix a given brane, a given object in the category, and look at its moduli space, its deformations. Or you can ask, can I deform the bulk theory itself? Can I deform the topological field theory itself? So that corresponds to deforming the category. And deforming the category is very closely related, if you have a compact generator, to deformations of associative algebras, except that I have to deform differential graded associative algebras. Right? So I guess I'm almost out of time. So let me just say what kind of theorems exist. So if C, so let C be a DG category, be a presentable then you can define a functor MC, and let's say smooth and proper. I haven't defined smooth and proper, so let me say what this means. This means that if C is equal to mod A, then properness is that A, homology of A is finite dimensional over K, and smoothness is that A is a perfect A by mod. It's a retract of something that's free, basically. So it's a very concrete condition. So if you have a smooth and proper DG category, actually you don't need the full strength of smooth and proper, but let me stick to that case. You can define, in any case, a functor from commutative DG algebras to spaces, which sends A to classifying space of compact objects in C tensor mod A. So then this is the theorem is that MC, so this theorem is first proved by Toine Bakier. And I gave a different proof. Later, in this special case, their theorem also applies to not smooth and proper but something called finite type. But I should say, what is this moduli space? This moduli space is the moduli of objects in C, which you should think of as the moduli of branes. So the theorem is that MC is a filtered union of n geometric stacks. And you can also compute, say, the tangent space, and you can guess what it will be. The tangent space of MC at some point E is just going to be the derived endomorphisms. So, which by the way, I forgot to say, the space of horns between two branes is just a space of string states stretching between those two branes. Strings starting and ending on these two boundary conditions in the physics interpretation. And the differential in this chain complex, Horn EF, is the BRST operator in the physics interpretation. So you have this moduli space of these boundary field theories, and you can ask, for example, if I put additional structures on C, do I get additional structures on the moduli space of objects? And you do. So for example, if you have something called a Calabi-Yau structure, which corresponds to the target space geometry being Calabi-Yau, then this moduli space carries something called a shifted symplectic structure. That was proved by Brav-Nikolov, and originally Toine suggested an approach. And in special cases, in the geometric case, goes back to Pantet, Toine, K, and Etsuzi. So this is kind of the prototype of a theorem of studying moduli spaces of quantum field theories. Maybe let me just finish with the last example, which is you can study deformations. You can ask, moduli of categories. And you can show that if C is a category, then there is a moduli problem, then you get this thing called the Hochschild homology of the category. And this is a differential graded Lie algebra. So in fact, it's an E2 algebra. And what is an E2 algebra? An E2 algebra is basically a locally constant factorization algebra. It's a structure you would find in the observables in a two-dimensional topological field theory. So this DGLA gives rise to a formal moduli problem. MC HH C. And it turns out that the naive deformation functor you define for categories doesn't quite satisfy the axioms that I wrote down. But what you can show is that if you're interested in deformations over formal, so this is a theorem we proved with Blank, Kazarkov, myself, that the deformations of C, so the naively defined deformations of C, when evaluated on formal power series ring, is isomorphic to solutions to Morakatan equations inside this formal power series. So again, this says that deformation of categories can be described explicitly, at least over formal power series rings, as solutions to Morakatan equations inside some E2 algebra. And this fits into a general paradigm. So you would expect some general picture where you have some moduli space of QFTs in general. So kind of hope or wish, which kind of, maybe I shouldn't call it a hope. I think physicists definitely believe or know this to be true. But it would be nice to make this more mathematically precise, to have kind of a moduli of QFTs in any dimension. And the general picture is supposed to be something like this. You have these, of course, conformal manifolds and various fixed points and you have these flows which connect the RG flow so this is the UV and IR. And one of the pictures that, if you look at the operational way that physics is done, as far as I understand it, you often study quantum field theory in this Wilsonian paradigm, where you start with some CFT and you flow along the RG flow to study effective theories. And one of the key things there is that if you have a fixed theory T, then the tangent space to the moduli space of QFT at T, at tau, let's say, should be isomorphic to local observables in tau. Right? So this is some heuristic picture, and I just showed you two concrete instantiations of this. So in the previous example, this E2 algebra is the local observables in a two-dimensional topological field theory, and I'm studying deformations of that theory, because the category is really, by Lurie's cobordism hypothesis, the category determines the two-dimensional theory. And similarly, if you go to the previous one, here I was studying moduli of boundary conditions, but branes. But branes are really boundary field theories. And so again, this theorem is expressing the tangent space, the space of boundary field theories, in terms of an E1 algebra. And this E1 algebra is observables in some, again, in some boundary theory. So, but I'm not sure if that's the right way to translate to physics. That's just my interpretation of it. But these mathematical statements are nevertheless true. So I'll stop there. Exactly 6. So thank you.